Hi guys, I think I have my mic off for the recording I just uploaded. So I'm gonna be uploading a new video, I guess. How unfortunate. Basically in the previous video I said we covered static and dynamic equilibrium, and in this video we're gonna cover qualitative equilibria. This is part 1 of 2 videos. So we're gonna be covering collision theory, rate of reaction, and how it relates to K, EQ, and Q. So collision theory, it's basically a set of principles, right? And it says you need to satisfy these principles or these requirements in order for a reaction to occur. And those two principles, namely, are that reactant particles must have sufficient energy when they collide, and the collision must be correctly oriented in order for a successful collision which can form products. So, collisions and rate of reaction are also directly proportional. So there's more collisions that you have, the higher the rate of reaction will be, and the less collisions you have, the lower the rate of reaction will be. And you can increase the collisions by increasing the temperature, which increases the average kinetic energy of particles. You can increase concentration of particles, which increases the net collisions. And you can also use the catalyst, which provides an alternate pathway of activation energy, which is lower. So, let me just quickly review this. For increased temperature, see this blue curve, that's increased temperature. Compared to the purple curve, which is reduced temperature, so LT for low temperature and HT for high temperature. The purple one, if you see here, you have this proportion of particles above activation energy. When you look at the blue one, you have this amount. The whole thing is just shifted, right? Because you're increasing the average kinetic energy. And so therefore, you have more successful collisions because more particles are above the proportions you need, the activation energy barrier. For the concentration of particles, it kind of like just makes sense, right? The net collisions are increased, so you have the probability of successful collisions stay the same, but since you have more collisions, there's going to be more successful collisions. And using a catalyst, which provides an alternate pathway of activation energy. So over here, you see how this is the uncatalyzed reaction, and this is the catalyzed reaction. Basically, see the uncatalyzed reaction, how like basically only these particles can react successfully because they have energy above this. But for the catalyzed reaction, like the activation energy is much lower, so you have all of these particles being able to react, which is a lot more than these ones. So yeah, that's why these three, basically, if you do these three, you can increase number of collisions, and by extension, you can increase the rate of reaction since they're directly proportional. Next, we look at collision theory and the relationship to equilibrium systems. So, in an equilibrium system, right, you basically have two reactions going on, right? You write one equation, but you're actually having two reactions. So this double arrow, it kind of represents both. So the forward reaction is reactants converting to products, and the reverse reaction is product converting to reactants, right? Now, going back to what we said about collision theory, what we can say is rate of reaction is proportional to the collisions, right? So what can we say about the forward rate of reaction then? Well, the collisions have to be between products and reactant particles, right? It depends which reaction you're looking at. So for the forward reaction, they have to be between reactant particles to form products. So therefore, the forward reaction rate is proportional, directly proportional to the concentration of the reactants, and for the reverse reaction rate, it's directly proportional to the concentration of the products, right? Because the products are falling back into reactants. And if we slap these two together on a fraction, we can measure the ratio of the concentrations at equilibrium, which gives you KEQ, which is the measurement of the ratio of products concentration to reactant concentration at equilibrium at a given temperature and constant temperature. Sorry. Okay, we know KQ. What is Q then? So Q and KQ have the same expression. Q is products over reactants, as well as KQ is also products over reactants, right? When I say products over reactants, I mean like concentration. But I'm not going to say that every time. So I'm going to just say this. So please remember this. What's the difference? KEQ measures the concentration of products to reactants at equilibrium, right? It's not at any other time. So let's say we have a reaction. Let's say equilibrium happens at 50 seconds. When we measure KEQ, we're taking the concentrations of these products and these reactants at 50 seconds, right? But for Q, it's like KEQ, but it's like you can just measure it whenever you want, basically. And it's very useful, actually, which I'll get to later, because it tells you where the reaction needs to proceed to, in which direction, for it to reach equilibrium. So for Q, right, it's the ratio of products to reactants at any given time. And both of these have to be kept at a constant temperature. It doesn't really matter what temperature it is, but as long as it doesn't change, then your K, EQ, and Q values won't change, because I'll get to this in the next lesson, but like KEQ and Q, they depend on temperature only, basically. Well, KEQ is. So, before I can show you guys the relationship between Q and KEQ and how you can use this to find a way to get to here, we're looking at how to calculate it, these expressions. So if we have this reaction, 2 moles of A plus 3 moles of B plus 4 moles of C, we can say the products are here and these are the reactants, right? Q is the concentration of the products over the concentration of the reactants, which is the concentration of C, right? What are we going to do with this stoichiometric coefficient? We're going to pull it to the power. Don't ask me why we do this. I don't really know why, but you just got to kind of do it. You feel me? So the reactants, you multiply the concentration if there's multiple constituents. So say if we had like plus 5D here, we would have D to the power of 5 here, and it will be multiplied in the middle. So like this. And for KEQ, it's the same thing, but again, you're only measuring the concentrations at equilibrium, not whenever you want. So keeping that in mind, now I can finally tell you guys about how you can use Q to figure out where the reaction needs to proceed to in order to reach KEQ. So, as we said, KEQ is at equilibrium, right? It's measured at equilibrium. And a reaction kept in a closed system will tend to equilibrium over time, right? If the conditions are met, which I mentioned in the last video. So, let's say for this reaction we have here. Let's just say the KEQ is here, right? In the middle. Now, let's just say there's a constant temperature of like this. It doesn't really matter, but as long as it doesn't change, I'm just saying it's constant, so KQ doesn't change. Now, what if we measure Q at some point and we say, oh, Q turns out to be here, right? Well, what does this mean? If we analyze the ratio, right? What is a ratio? Oh, I didn't mean to write that. Basically, a ratio is a fraction, right? And what happens when the fraction is large? Two things, right? It's either that the numerator is large or the denominator is small, right? So, in this case, Q is less than KEQ, right? So that means KEQ is larger. So that means the products in this sense will have, there will be more products concentration in KEQ, and there'll be less reactants concentration in KEQ. However, since Q is lower, right, there's going to be a higher amount of reactants and a lower amount of products, right? Because that makes the fraction smaller. And since KEQ is larger than Q, then the fraction will be smaller, and therefore there's going to be less products and more reactants. Now, what do you guys think this means? Basically, since Q is less than KEQ, it wants to reach KEQ. It wants to reach equilibrium, right? So, how do we do this? in which direction do we move on the number line? We want to move this way, right? We want to move right? So, in order to move right, what happens? Well, if we consider the reaction over here, right? That's reactants over here. And these are products. Well, there's one product. But when we say shift to the right, in this sense, the arrow is pointing this way, right? When we shift to the right, what we're doing is we're favoring the forward reaction. And we're producing more products, right? So we want to produce more of this, which only happens when we favor the forward reaction. So in this case, when Q is less than KEQ, forward reaction is favored. And the system shifts to the right. You can say that. Now, what if we switch the position of these two? What if KQ was here? And we measure Q and it turned out to be here. Well, now that Q is larger than KQ, right? We can say for certain that there's a higher concentration of products in Q compared to the products in KQ. So what does this mean? Q has to move all the way back down here to reach KEQ, right? So if we look back at the reaction, what does shifting left mean? You follow this arrow, the one that points left, right? And shifting left means you're favoring the production of reactants. So in this case, the reaction shift proceeds favoring reverse to produce reactants, right? And what happens is, once this happens, right? Like this is called a shift to the left. Now, there's one last case. This case is quite obvious, but what if this is KQ, and what if you measure Q at some random time, and it ends up to be the exact same value as KQ? What does that mean? If Q is equal to KEQ, then the system is at equilibrium. And yeah, it won't change unless it's been disturbed. So, in this lesson we covered Q, KEQ, collision theory, rate of reaction, and how it relates to Q and KEQ. So, sorry about the mic incident, but I'll try to make it doesn't happen next time. In the next video, I'll be doing the same topic, but I'll be teaching you guys Le Chatelier's principle and how to analyze equilibrium graphs qualitatively, which are two pretty big things. So it might be a bit longer. So yeah, thank you guys.